Okay, very good. In this lecture, we're going to continue our studies of information geometry. So the basic idea, let me just remind ourselves what we were doing last class, is if you have a statistical manifold, and we're going to use parameters theta as coordinates. So the statistical manifold is the family of all probability distributions of some variable parameterized by some thetas, which we're going to use as parameters. So one of these points here on this space with coordinates theta 1, theta 2 represents a probability distribution. What we found is that the distance between any two probability distributions, so if we have theta and we have another probability distribution here, theta plus the theta, you can compute the distance between those two, and that is given by a form of Pythagoras theorem written in this way, where the metric tensor is the information metric, and this is going to be given by dx, the probability of x given theta, and here we have the derivative of the log of p with respect to theta a, derivative of the log of p with respect to theta b. Very good. So that's what we did last time. This is in the case where the x's are continuous variables. For the discrete case, where we have, instead of x, we have maybe a simplex or something like that, where x is discrete, we get something like this. The metric is the sum over all values of I of pi given theta, the log pi given theta, the theta a, the log pi given theta, differentiate with respect to theta b. Very good. There is general comment. There is an overall factor here, a multiplication factor here, that's undetermined by the remarks that we have made in the past. And we are going to see that that factor is really a freedom. And it's basically the freedom you have in choosing the units of distance. Whether you use one unit of distance or another, you're going to see that these factors here can actually change. And we're going to address that very interesting question later today. If we write the information metric in this way, what are the units of distance that we are implicitly assuming? But that's a question for later. Before we proceed, a simple example may be useful. So here's an example. Oh, come on. There we go. Suppose we are dealing with a simplex, and the simplex is such that the probabilities here are normalized, and we use as parameters the choice for parameters of probability distributions. You can choose whatever you want. It's any set of coordinates will work as well as any other set. We showed that this object here transforms as a tensor, and if this transforms as a tensor and those transform as little vectors, then the transformations all cancel out in such a way that the actual distance is invariant. This is ultimately why we care about distances. It doesn't matter what coordinates you use. But in any case, let's keep going. Suppose that use as parameters those coordinates on the statistical manifold, use the probabilities themselves. So we're going to have, if we have n values of these probabilities, so that we're dealing with an n minus 1 simplex, then we're going to have as many parameters as probabilities. And if we do that, then the metric tensor takes the following form. So I'm just going to rewrite this equation here and there, and we're going to have pi d log pi with respect to p a. That's the theta a. And the next factor is the log pi with respect to p b. Let us compute pi. The derivative of log pi is 1 over pi. Derivative of pi with respect to pa. That's just a Kronecker delta ia. And the derivative there is going to be 1 over pi again, Kronecker ib. Let us do the sum. Of course, some of these things are going to cancel out. And what we get here is Ga. Let's see, there is the sum over I, delta ia, pi, delta ib. If I do the sum over I, the summation, can use this delta here to do the sum. It contributes when you get a contribution when I equals A. So then you get 1. And if I put I equals A there, what I get for the metric is delta AB over PA. And that's a form that we derived, a form of the metric that we derived by assuming that you had the simplex embedded in a space that had Euclidean geometry, a flat space. So you can see that all of these formulas are internally consistent. Very good. So for the special case of the simplex, we have a very nice simple formula. For the general case, we have formulas of this type. Very good. So what I would like to address now, oh yes, there was another formula we had for the entropy from entropy, right? The connection to entropy. If you have the entropy of two probability distributions, one minus one labeled by theta prime and the other labeled by theta, we saw that we had another formula for the metric tensor that had to do with taking the second derivatives of this entropy with respect to theta prime A, theta prime B, and evaluating at theta equals theta prime prime, theta prime equals theta. So the idea was if you do a Taylor expansion of this entropy here, the very first term vanishes because this vanishes when theta equals theta prime. The next term vanishes because theta equals theta prime is the maximum. The first non-leading term is going to be given by the second derivative, and that's what gives you the measure of distance. So this is another interesting way of thinking about what this metric is doing. Very good. Enough of a review of what we were doing last time. The main objection, if anything, that we had against this expression for the metric is that we derived it by either invoking intuitions about distinguishability or intuitions about embedding the space of probability distributions in a flat space, or even about taking derivatives of the entropy. All of those are presumably nicely intuitive approaches to what it is that we're doing, but it leaves the question of uniqueness. And the crucial theorem on this matter is a theorem by Chentsov. Let me see the year. When did he do this? 1981. So Chentsov, Russian guy, 1981. Managed to prove that this metric is essentially unique up to an overall factor that is just determining what the units are. So the metric is universal and unique, and that's what makes it important. If you are talking about probability distributions, the space of probability distributions has one and only one notion of metric geometry, which is something we want to exploit. The proof that I have in my lecture notes is due to Campbell in 1986. And what the basic theorem that these guys ended up proving was that if you imposing invariance under Markovian embeddings implies the Fisher-Rao metric. So that's the main theorem in this. And so what we have to understand, I'm not gonna go over the details of the proof. You can read it in the book if you feel so inclined. What I want you to understand is the basic idea of what it is that's being imposed here. There is a symmetry principle that's being imposed, and the transformations are these Markovian embeddings, so we have to understand what they are. And most importantly, what we have to understand is why are these symmetries so natural in the context of statistical manifolds. You see, the thing is, if you have a manifold and a manifold has points, a genetic manifold, there is no notion of distance associated to manifolds. You have to bring it from the outside. You have to impose something additional on the manifold, some additional structure. Here, the structure comes hardwired. You don't have to impose it. It's there by virtue of these things being, of the points representing probability distributions. And the way this works is as follows. First, we're going to simplify the whole idea by considering discrete probabilities. So the idea is, if you were to have a continuum, continuous probabilities, something like that, you can always approximate the distribution by just doing discretizing and considering the probability in a tiny, in a small bin. You call that pi and proceed. So the idea here is that you're going from a continuum to a discrete distribution, and the spaces, the statistical manifolds we're going to be dealing are simplexes. As you can probably appreciate, the idea here is that going to discrete probabilities is not going to be a serious problem, because you can always bin your space in smaller and smaller cells, choose as large a simplex as you want, and proceed. Of course, there are going to be subtleties that arise in the limits, but as all times when you're actually doing sciences and you're doing physics in particular, the problems with discretization can always be resolved by looking at the physics of the problem that you're actually handling and making sure that the appropriate information is being included or not included in the limiting process. We saw, for example, that by trying to generalize the Shannon entropy to continuous distributions, you would run into trouble. So the way to avoid that was to recognize that you would run into trouble and invent a notion of relative entropy that was an entropy relative to an underlying measure. So you can always fix those problems. In this particular case of the metric, no problems arise. So those problems are safe. Very good. So first thing, consider discrete probabilities. Second thing, we have to understand what Markovian mappings are. So first, let us, so we're dealing with simplices. We deal with a simplex, and remember the simplexes are going to be such that you have several of these guys, and the probabilities are up to 1. But what we would like to understand next is what are these Markovian embeddings. To do that, first let's just understand a little bit about what a coarse graining is. Or a grouping. The idea here is, if you have a probability distribution, so here we have a probability distribution for a 3-sided die, which is a 2 simplex. Then we do a coarse graining, and this is what the coarse graining is. When we take, for example, these two, say outcomes 1 or 2 count as heads, outcome 3 counts as tails. And so here we're going to write the probability of heads. Let me write it like this, wait, before I do this. P1 plus P2 and P3. We call this heads, call that tails. And so what we have here is a probability, is a simplex also of, in this particular case, 1 dimension less. And the values that appear here or something like that. Very good. So we see that by doing coarse grainings or groupings, we can go from a simplex of higher dimension to a simplex of a lower dimension. So this is going from the 2 simplex to the 1 simplex. Okay, a Markovian embedding is going in the opposite direction. Okay. A Markovian embedding is one that would allow us to go from the 1 simplex to the 2 simplex. So what we're doing is we are embedding the 1 simplex in a 2 simplex. We're gonna draw this a few times. So for example, we could go here to, since here we were just adding, we could, well, yeah, I'll write it here. We could choose the following. 1/2, 1/2, and 1 minus p. So when we have something like this, you can see that if you add those two, like here, we add those two, we call that p, we add those two, we get p. And then the remaining one is the appropriate p3. So what we have done here is we have taken a simplex. Here is the one-dimensional simplex. P goes from 0 to 1. And what we have done is we have embedded it here. We have the 3 axis, we have the simplex there, and what we have done is we have embedded the simplex here embedded a coin in a 3-sided die, right? This is the particular case in which P1 is equal to P2 and P1 plus P2 is equal to the P. When you are down here, P, which is P1 plus P2, is equal to 1. When you are up there, so this is this applies to the whole line, right, including that point there. When you are out there, 1 minus P3, sorry, when you're up there, P is equal to 0, and of course P3, which is 1 minus P, is equal to 1. Okay, so this is what the embedding is. But now one of the things that you can immediately see is that the embedding is not unique. So we can definitely embed P1 minus P into 1/2 P, 1/2 P, 1 minus P. Let's call this A. But you can also, well, let me put the A here. We can also, we can put here 2/3. Well, let me see. Yes, 2/3. 1/3 P, 1 minus P. And these two, if you add those two, you also get P. And in fact, you can do whatever you want here. You see that you have an infinite way, an infinite number of ways of embedding the 1 simplex into the 2 simplex. This is the first embedding. In the second embedding, if you think a little bit more about it, you can see that it corresponds to that line. And depending on how you choose these coefficients, the 1/2 or the 2/3 and 1/3, you can actually move this line anywhere you want on this. Well, you can just move it any way you want. There's an infinite number of ways of doing this. In fact, you can also embed this in any other way you want. Nothing prevents you from embedding in lines like that. It's up to you. So now why do we care about these Markovian embeddings? Because what we are trying to do here, so let me this is the crucial thing. Remember what we're trying to do. What we're trying to do is we're trying to figure out what happens with these probabilities. One thing we could do is group them. And what that allows you to do is go from high dimensions to low dimensions. You can always do that. If you try to go in the opposite direction, you see that there is an incredible amount of freedom in how you do the embedding. But the whole point of this is that if you're trying to figure out the distance between those two probability distributions, and you embed this simplex into this higher dimensional simplex, well then the two probability distributions are going to be there. And the idea is that if these two probability distributions, if you're trying to figure out how distinguishable they are, and the measure of distinguishability, it doesn't much matter if you have figured out how distinguishable they are in this space or in this space. It doesn't matter if you think how distinguishable they are when you consider them as two probability distributions on this line, or when you consider them as two probability distributions on the whole simplex. If you're trying to define a distance, and the distance here is given by the one-dimensional Pythagoras theorem, namely something like that, okay, just one-dimensional, and you're trying to do exactly the same thing over there, here you're going to have something like that, right? The Pythagoras theorems or whatever they are. Anyway, the whole point of this idea is that you can use Pythagoras theorem here, or you can use Pythagoras theorem there. You should get the same distance. Why? Because distance is distinguishability. That's the point. If you have this probability distribution and that probability distribution, and you compute the relative entropy, it doesn't matter if you compute the relative entropy here or there. The relative entropy, the degree to which one is ranked favorable or preferred over the other is always going to be the same. And in fact, it should also be the same if you do this other embedding or any other embedding that you may want to do. But now you see what this is what we mean by invariance under Markovian embeddings. Under Markovian embeddings, the distance in situation 1 is the same as the distance, or rather, the distance in the one simplex is the same as the distance in the two simplex. And that, of course, imposes a certain constraint on what metric tensors you're going to choose here. Here, the metric tensor is pretty, it appears to be pretty simple, right? Because this is just one dimension. But the metric tensor here is not nearly as simple, but the two have to give the same distance. Why is this very constraining? The reason that this is constraining is that having embedded the one simplex into a two simplex, you can go ahead and embed the two simplex into a three simplex, into a four simplex, into a five simplex. You can keep embedding in higher and higher dimensions, and you should always get the same distance. Now, at this point, you should start to get nervous, right? Because if you're trying to determine a formula for Pythagoras theorem, and you have one constraint, you say, sure, yeah, maybe I can do it. But if you have an infinite number of constraints, because you can keep embedding in higher and higher dimensions, then you have an infinite number of constraints. There is no guarantee that you're going to get an answer. You may have constrained yourself so much that there is no possible metric tensor that's going to satisfy these requirements. So this is an infinite number. An infinite number of constraints. The theorem says that impose this invariance leads to the Fisher Rao metric. Why is why is this invariance something you want to impose? The reason, if you go back to our discussion of coarse grainings, is that if you have a three-sided die, then you can make that three-sided die work as a two-sided die, a coin. And therefore, if you figure out the probability, the distance between two probabilities here, you should be able to figure out the probabilities of this on this side, where you're dealing with a three-sided die or a two-sided die, and you should get the same answer. And of course, you can go backwards. That's what we do with the embeddings, and you can keep going. It's a truly inevitable property or a symmetry that you're not going to find for other manifolds. This is the kind of symmetry that would only appear if you're dealing with probability distributions. Very good. So this is the result. The theorem says that, here it is. The theorem of Chentsov and Campbell says that if you impose invariance under these Markovian embeddings, you get the Fisher Rao metric. Very good. Enough of that. I hope you are satisfied that these are symmetries we want to impose if we're truly talking about probability theory. And now that we have made that statement that indeed the metric is unique, let's use it. Very good. I want to use this first First, I would like to point out something interesting about the information metric, namely that this gives a dimensionless distance. Let us look at the distance. We'll write it. I'm just writing out the formulas again in terms of the parameters, and the metric tensor is dx p, and then I have the log p d theta, the log p d theta. Very good. Look at this expression here. What this expression here involves is dx which is a probability, right? It is a probability that x lands within this small region indicated by the x. So this being a probability has no units. It is dimensionless. So now the log, of course, has no dimensions. And so here we have dd theta. What this dd theta here has is dimensions of 1 over theta. But when I multiply by d theta here, the units of theta cancel out. Similarly, the units are, this is a b, the units of this theta cancel out. The conclusion is that dl squared has no units. This is remarkable on several levels. Let's explore a little bit what this is. The first reaction should be, what? I mean, shouldn't distance have units of distance? What on earth is going on? Very well. To figure out what actually is happening, consider an example. We're going to discuss the metric, find the metric for Gaussians. So suppose we have 3D Gaussians, okay? Could be in any dimensions, but 3D Gaussians of mean theta and variance. So let me write the mean here. The mean of x a is theta a, and the variance is sigma squared. So these Gaussians all have the same sigma. It's isotropic. It's a spherically symmetric Gaussian. The 3 will play no role, absolutely, just for definiteness. So what are these probability distributions? These probability distributions are going to be there are some factors here. Am I getting this wrong? Let me get the normalization factor. There is a 3/2 there somewhere. And I'll see if I can find it. Otherwise, I'll just fix it for later. Yes. So this is 3/2. And then there is the exponential. And there are 3 of these terms. xa minus theta a, xb minus theta b, and I'm summing over a and b. So you can see that the 3 components x, y, z for a equal being 1, 2, 3, right? X, y, z, they're completely independent of each other. So this is the product of three Gaussians. So what we would like to do now is compute the metric associated to this family of probability distributions. Sigma is fixed, so it's not a parameter here. The only parameters are the mean values. So we're going to compute the log of p, and we're going to take the derivative with respect to theta c. And so we do the derivative theta c of the log minus the log of 2 pi sigma squared multiplied by 3/2. So that's the log of the first piece, and then there is the log of the second piece minus delta AB to sigma squared x minus theta x minus theta. Very good. There you go. So this is going to be one of the derivatives that appears here. When we differentiate this first piece with respect to theta c, there is no theta c there, so that guy goes away. And when we differentiate this other piece here, we're going to have to differentiate the theta a, and we're going to have to differentiate the theta b. When we differentiate the theta a with respect to theta c, we're going to, well, it only contributes, when I'm summing over a, it only contributes when I have a equals c. If a is equal to c, then b must be equal to c as well. And we have minus 1 over 2 sigma squared. And then the derivative here has a minus and a minus, so that's a plus. And the derivative of theta with respect to theta c is going to be a 1 when a equals c. And we get the other term. But now it only contributes when theta is equal to c. Same thing when I take the derivative with respect to theta b. It only contributes when b equals to c, in which case this guy becomes c, and I cancel the factor of 2. So that's the derivative. So we're going to substitute over here. When I substitute over there, I'm going to have the metric is going to be equal to dx, that is p, in this case it's 3 dimensions, so that's 3d3x. The first term is going to be theta a, and this is all divided by sigma squared. So I'm going to write the sigma squared out here, but there are 2 of these guys. So there is a sigma 4. When you look at this expression here, you see that when a is equal to b, what you have here is the variance, sigma 4. Okay, when a is equal to b, you get the variance, which is going to be sigma squared. And when you have a different from b, if a is different from b, remember these are Gaussians. These are Gaussians. And this is a product of 3 different Gaussians. So when a is different from b, you're going to get the expected value of the first term multiplied by the expected value of the second term, and those expected values vanish. So what you have is sigma squared when a equals b, 0 otherwise. So the metric tensor takes this very nice form, sigma squared, which means that the distance between 2 Gaussians between two Gaussians that differ in their means is equal to that. That's the result I wanted to bring to you. Now, this result is remarkable on many levels, and we'll milk it because this result, it's actually going to be pretty interesting. It has features that are of universal validity. Look at what's going on here. What we have here is the Euclidean distance, whatever that might be. It's Pythagoras theorem. So indeed, the space of probability distributions of Gaussians obeys Pythagoras theorem. But if this is the Euclidean distance in whatever units you're using, look at what you have down here, sigma squared. If A is measured, if theta A is measured in meters, so up here you have meter squared, and down here, this is the variance of the thetas, right? You have meter squared too. So now you see why the distance, the L, the information distance is dimensionless. It's because the information distance, the information metric, measures distance in units of the uncertainty sigma. Those are the units that are being expressed when you use the information metric here. I computed it here for Gaussians, but this is actually general, not just for Gaussians. This is universal. In general. Not just for Gaussians. Very interesting. Comments? So here we have an interesting result here. The metric for the geometry of the statistical manifold of Gaussians with given sigma is Euclidean. This is a result that I find particularly provocative. And what I mean by this is the following. Consider real three-dimensional space. If it were the case that because of quantum fluctuations or whatever fluctuations, be it caused by space-time foam or maybe by string quantum fluctuations or quantum loops, whatever the reason, if it is true that the geometry of space is such that points in space are blurred for any particular reason, so if points in space, in physical space, are blurred for any physical reason, and in particular, if you believe in central limit theorems, if whatever the blur is, it arises from the contribution of very, very many small perturbations that are happening at much smaller distances, then it is to be expected that the blur of these points is going to be Gaussian. If the points in physical space are blurred as Gaussians, and this is very possible invoking central limit theorems, then we expect the geometry of space to be Euclidean. I hope you appreciate the significance of this. The fact that the geometry of the space we seem to inhabit is Euclidean and that this space is flat might be a consequence of space actually having some kind of structure at very small distances that makes points in space be blurred. This is one of the facts that has led me to be very enthusiastic about the possibility or the potential of using information geometry methods within physics. Now this is a big if, right? But it's definitely something worth pursuing. Very good. Next interesting remark that we would like to make here. Let me see. First remark, the information metric measures distance in units of the uncertainty. The geometry of Gaussians is Euclidean. Possible physics, oh, well, I'll leave it there. Possible physics consequence. Sometimes my pen does not write. Very good, now it did. Another consequence, yes. What is the length of a curve? Suppose you have a curve in this space of Gaussians and distance is measured in units of sigma. What that means is that we essentially are saying one point and another point are going to be, if they are distinguishable, so here is one point, and this is another point, and this is another point. If these points have a blur, have a size of radius sigma, then we can essentially, or a size of sigma, we can essentially measure the length by counting the number of distinguishable points. So can be measured by counting the number of distinguishable points. By the way, this is general too. It's not just for Gaussians, okay? What gets really weird is that then we can do something else, which is if you have an area, you can figure out the area by counting measure area by counting the number of distinguishable points. Same thing. And now this gets like really weird, because you say, wait a minute, this length has 17 points. This area has 12. We can actually say that this length is bigger than this area. We can compare the measures for objects of different dimensionality. We can compare a length with an area, with a volume. So this is the fact that this distance is dimensionless, because it comes measured in the number of, in the size of these blurred points, means that you can compare areas and volumes, which is something that, of course, normally you can't do when you have structureless points. And these points are not structureless, right? They're blurred. They have a size, right? The moment that you have these structureless points, you lose the ability of comparing objects of different dimensions. But when you're figuring out what these are probability distributions, and you can actually have a criterion for deciding whether one is distinguishable from another or not, then you can compare them, and you have something very interesting, because that means that statistical manifolds, let me just write the previous interesting consequence. We can compare lengths with areas with volumes. Now, I do not know that that is particularly useful. I haven't thought of anything useful to do. This comes from from lengths being, from distances being dimensionless. But one of the things that this is actually indicating is that these statistical manifolds have properties, have geometrical properties that are obviously associated to a continuum, right? We can vary the parameters theta continuously, right? Have properties of the continuum and also properties that you typically would associate with discrete structures, like a lattice. The points that are distinguishable are definitely separate from each other and of discrete spaces. If one were to try to formulate a field theory on top of a space of blurred points, then it would not make much sense to have wavelengths that are smaller than the blur. And what that means is that all those problems of infinities that typically arise in quantum field theories would not be absent in such spaces. So this is also an important potential contribution that there may be in treating the geometry of space as the information geometry of statistical manifolds. But of course, these theories have not been developed. This is just consequences of spaces of probability distributions. But physical theories that incorporate these ideas have not yet been developed. That's for the future. And maybe this is a good time to stop here. I guess that this is basically all I needed to say about information geometry before we now start using it to do more inference. See you in a while.